Hey there, Grade 9 geometry students of St. Paul American School Clark. Welcome to this Explainer. Today, we're jumping right into Unit 1, Lesson 4, Formal Constructions and the Foundations of Proof. We're about to dive into the literal bedrock of mathematical logic. We're talking about building perfect shapes and lines, not by eyeballing it, not by guessing, but by using absolute, unbreakable rules. Let's get started.
Section 1. Our objective: mastering formal geometric constructions.
So, when you hear the phrase formal construction, I really want you to picture a super strict set of rules. We actually have to completely strip away the tools you're probably most used to using. Seriously, in this specific mathematical game, numbers are completely banned. No way around it. If you catch yourself relying on a measurement, like saying, oh, this is 5 centimeters or 2 inches, well, you've already broken the rules.
Right, so if we can't use numbers, what exactly are we doing here? Well, doing a formal geometric construction means you're literally only allowed to use two very specific tools. You've got your compass, that little metal tool with a sharp point and a pencil, and a straight edge. That's it, nothing else. And yet you're going to use just those two simple items to draw incredibly complex, perfectly precise geometric shapes.
This whole philosophy illustrates something pretty incredible about math. Like the text says, this is the quote-unquote pure form of geometry. By completely throwing out numbers, it forces us to rely entirely on logic instead of physical measurements. And honestly, this is a massive shift in how you think. Instead of measuring an angle to check if it's 90 degrees, you're using the totally unarguable logic of intersecting circles to guarantee it's 90 degrees. This exact mindset is what lays the groundwork for basically all future mathematical proof.
Moving on to Section 2, Process Demonstration. Let's take a look at a segment bisector.
Okay, so because we can't just write down a measurement to prove our work, we use what's called a process demonstration. That just means showing every single visual step, so anyone looking at your paper can clearly see the logical path you took. Let's see how this works in practice to bisect a segment, which just means cutting it perfectly in half. First up, open your compass so it's wider than half the segment's length. Then place that sharp metal point perfectly on one end of the segment and draw arcs above and below the line. You'll see those dashed lines representing the exact path of your compass pencil. Now for step 3. Listen, here is the absolute most important rule. Do not change the width of your compass. Seriously, keep it locked exactly as it was. Now, just move that metal point over to the other end of the segment and draw intersecting arcs above and below the line again. See where those two sets of arcs cross each other? Right there, you have found pure, unmeasured perfection.
Finally, grab your straight edge. Just line it up directed with those two exact intersections where the arcs cross above and below your original segment and draw a line connecting them. Boom! You've now perfectly bisected the original segment, cutting it exactly in half. And you did it without ever once measuring it with a number. You literally proved it was exactly in the middle just by using the symmetrical logic of those compass arcs.
Section 3. Misconception check. Before you go off and practice these process demonstrations on your own, we really need to clear something up.
The crucial point here is understanding the real difference between a straight edge and a ruler. A straight edge is a tool used strictly for drawing perfectly straight lines. Now, you might actually be holding a standard ruler in your hand right now, and hey, that's totally fine, but you have to treat it only as a straight edge. All those little numbers printed on it, you gotta pretend they just don't exist. Using the ruler to measure distances with numbers totally breaks the purity of the construction. Basically, a ruler tempts you to measure, a straight edge forces you to prove.
All right, Section 4, Formative check. Let's pause for a quick check to see if we've really got a handle on this.
Think back to step 1 of our process demonstration. I made a really specific point of saying you must open the compass to a width that is more than half the length of your segment. So why do you think that's absolutely required? Like, what would actually happen if you didn't do that? Take a quick second to visualize it. Well, if you guessed that the arcs wouldn't cross otherwise, you hit the nail on the head. You're exactly right. If your compass is open to less than halfway, you're just going to draw an arc on the left, an arc on the right, and you'll be left with this big, empty gap in the middle. They'll literally never touch. This kind of logic, anticipating how the shapes have to interact and proving it works without relying on numbers, that is the exact foundation of geometric proof we're talking about.
Section 5, Final Recap. Let's wrap things up and review the core rules we've established today.
Keep these 3 main pillars in mind for your assignments. Number 1, pure construction relies strictly on a compass and a straight edge. Number 2, numbers are banned. If you measure anything, you've gone off track. And number 3, Process demonstrations are your ultimate proof. You absolutely must visually leave every single arc and mark on the page to make your logic undeniably clear to anyone looking at it.
I'm going to leave you with this thought as you head into your geometry assignments for St. Paul American School Clark today. How does relying only on intersecting arcs actually create a more airtight, mathematically sound proof than using a ruler ever could? Really think about the flaws of human measurement versus the absolute truth of mathematical logic. Have a great time exploring this pure geometry, and I will see you in the next explainer.